So we were talking about analog to digital converters in that integrating type. Just before integrating type, we have studied something called flash. So what is the problem in flash, Nishant? What do you think?
Flash is fastest.
So that's the like advantages. Advantage,
but
Look, we care about only the area, power,
areas, number of NAND gates.
NAND gates. It's only about NAND gates, or look, digital will not take much power or area. Why? What do you think? Yeah, so 2 to power n minus 1 number of comparators are needed, and all are in parallel, all are active all the time. So power is 2 raised to n minus 1 times power of comparator. And thereafter, of course, digital will take some power, but that will be like very small. If the whole thing is taking milliwatts of power, then that one is going to take 1 microwatt of power, 1,000 times lesser than that. So that's why like we don't care much about that. But flash is going to take much area with higher power consumption, which is analog side. So that's why we don't take flash. However, if number of bits are very low, like 2 to 3 bits or maybe 4 bits, then you can use flash if you want very fast operation. However, there is another class of ADC which is integrating type, where there might be like dual slope ADC. Here, do you find any problem, or what is the like this particular class of ADC, flash ADC, is coming under very high speed, right? Or you can do high frequency operation, right? Because it's fast, it's a parallel. So, what do you think about this dual slope? Infinite? No, not infinite. Significant. Okay, significant. So, so what do you mean by significant now? Like, still we have not become engineer. If you remember, we were trying to ramp up the signal for fixed amount of time, that T1 was depending on 2 raised to n times T clock, where n is the like number of bits which you want to evaluate, and 2 raised to n times you are running the counter, and you integrate with the assumption that it has the constant current. So this is T1 is 2 raised to n times T clock. Here answer was coming in 1 T clock, right? After 1 T clock, the analog input is converted to digital. However, in dual slope, it takes more than 2 raised to n T clock, because right now it's not converted yet. It needs to be come down also. And after T2, which is T1 plus T2 time, you will have availability of analog to digital output. If this input is VDD, completely VDD, then T1 and T2 both will be equal, and that will be equal to this one. So this much amount of time you need. So can you tell me, in the worst case, if you are designing 7 bits of ADC, how much time do you require to convert analog signal to a digital signal? 5 256, or you're saying 2 to power 8 T clock, yeah, that is what you require. So it's 2 raised to n plus 1 times t clock. That's the required. So this is going to take more time in terms of like, even if your clock is very fast as high as 1 GSPS, this is going to take more time, right? So this whole thing will be divided by 512 times to find out the effective conversion time. So there are two things, if I forgot to tell you. There is something called sampling time, which might be high, which is known as t clock. There is something called conversion time. Conversion time may be anything, may not be same as sampling time. If it is equal to sampling time, means it's a flash ADC or it's parallel ADC. But in the case of this one, it will take, let's say, 2 raised to n times t clock. Just for your information, there is one more thing. When we are doing all such things, we would like to make sure that, let's say, this is an ADC. Whose symbol looks like this one, where analog is an input and output is digital. So when you are doing this, this analog input is actually V in star. Star means it's sampled input or it's discrete input. So whatever the conversion time needed here, it will be one extra clock cycle needed because of the switch. So as many number of switches you are adding in a path, as many number of t clock you need extra. So do not add many switches if it is not required, first of all, right? Or if you can club this somewhere inside the ADC logic, then it's advantageous. But as you are studying at the beginning level, generally this is one sampling clock is needed on top of 2 raised to n number of t clock for the case of integrating type ADC or the dual stop ADC. So now you can see that if you, even if you are working at 1 GSPS, what is the conversion time? Can you tell me?
Sir, we should take conversion as 2 raised to n or 2 raised to n plus omega 4.
No, 2 raised to n plus, sorry. Hmm? Can you give me the number, direct number, something in megahertz, kilohertz, anything, whatever is coming? Can you tell me that for 8 bits, right? Or let's make it 9 bits so that it's easy for you. So approximately 1000 times 1 GSPS. So this number is coming around at how much? 1 mega. So yeah, in 1 microsecond, right? Right?
1.024.
Yeah, so 1.024 approximated to 1 microsecond. And one more sampling time, which is in nanosecond, so plus 1 nanosecond. That much time you are going to spend. If it is flash ADC, it's going to take 1 nanosecond at cost of area as well as power, and this is going to take 1 microsecond. So you can understand this 1 GSPS we are not going to use ever, first of all. This sampling might be 1 megahertz, right? 1 MSPS. That is the real thing, because somebody has to give you 1 gigahertz of signal also. So you need to have somebody who can give you PLL of 1 gigahertz. Or do you know any function generator which can give you 1 gigahertz available in IIT Mandi's laboratory? So when I was doing my PhD, I needed 1 gigahertz. So we ordered one pulse pattern generator, which can give 1 gigahertz, actually 3 gigahertz, but whose price was just 75,000 just to get 1 giga. So you can understand it's an expensive business if you want 1 giga. So 1 giga is not available to me at straight away. In our function generator, you can see even though we are spending something like 1 lakh rupees or 2 lakh rupees of function generator, all new function generators are very expensive. If you have seen the older one, the new one are much better, and they are expensive also, and those can give you maybe 10 megahertz, right? So if you have 10 megahertz signal is available, if you are designing 9 bits, you may land up with something like, so this will be almost 100 kilo, 10 kilo, right? This is 10 kilohertz thing, right? So this is the way this particular ADC can give you the slow speed only. It cannot achieve, if you want to make something to have the conversion time of 1 GSPS, what do you think? Is it doable or not doable? For 1 GSPS of conversion time, what T clock I need for 9 bits? 1 terahertz, approximately 1 terahertz. So that is the limitation. We cannot do that with such ADC structure, right? And one more thing. So again, revisiting what we were talking about. So during phase 5.1, this is connected, this is not connected. this is this is a mistake I found out. It has to be off. This S2 has to be on when actually you are starting new new data, or you are sampling with the new value. Then you should make the S2 off, S2 on. So at the beginning we are keeping C1 at 0 charge at both sides. When it's connected to minus V in, this Vx point is going to reach V in, but as it is like minus side, though its integration is minus R C1, right? Going from, let's say, 0 to T, you're going to have minus V in, right? So this way you can integrate it at the first instance. Vx will reach at V in after RC time constant. This is the meaning of this, right? After V in time, after R1 C1 times, Vx is equal to V in. Now at the time, output of this one is 0, right? Output of this one is 0, and this is happening in T1 time, which is equal to 2 raised to n times T clock. This fixed. This is phase 5.1, which is having the duration of 2 raised to n times T clock, and once it reaches the value of V in, so the counter will stop counting, everything will be stopped. The only thing is, afterwards we will end up in phase 2, where S1 is off, or it is connected to Vref. This is also off. Now this value is already at V in right now. Capacitor is charged at V in. When you are connecting at Vref, that might be equal to V in, or it might be less than some V in value. So this Vx value will try to reach Vref value. So when it reaches Vref, it stopped, and this value, or we can say that when Vref reaches here, it's not shown here, but in reality it says that this is actually one time this value was reaching minus V in actually, and another time when you are adding some plus value, it's keep on trying to reach 0. When it reaches 0, this becomes 1. When this becomes 1, again this counter will start, sorry, till that time these bits will be counted in downside. In earlier case it was up, in another side it's down, and the difference of these two will be converted as bits here, and that will be available at the output. This is what happened. So there was one mistake. I kept it. It has to be off. So it follows this way. But whenever it reaches 0 or below 0, the output is actually 1. Okay. So we talked about this. We talked about this also. So on top of this, if your input is not just a DC value, but when you are having this sampling business is going on, V in, when it's sampled, you are actually afterwards integrating this. So what is happening? You are trying to integrate a rectangular signal. So in frequency domain, you are going to see something like this, which is known as sinc function or sin x by x. This is basically we are calling sinc function, right? So this is an advantageous thing, and also I told you, even though we are drawing this way, but when you are going to do the simulation, you are going to see only positive side only, or you can see something like this, right? Because it's mod of h of j omega, so it's plus side only. Now the question is, okay, by the way, this is valid when V is not just a constant quantity, it's moving on. So now, if the input signal V is a DC level with power line noise of 50 Hz superimposed on it, choose T1 to filter out the power line noise. Yeah. So this was the question I gave you last time. So what do you think? Hmm? Okay. So you are taking T1 is equal to 1 by 50, is it? And you are saying that it has to be less than 2 millisecond or exactly 2 millisecond. If it is less than, then the problem is you are still going to see all this noise. Hmm? Yeah, it should be T1, not less or greater, right? Because as Saurav is suggesting, we want to make 50, 100, 150, so that 50 is coming here, exactly here, right? Right? We understand why 50 hertz, by the way, right? Other than Siddhant, we all understand, right? What is 50 hertz is? What is 50 hertz, by the way? How this 50 hertz is coming? So power line frequency, how this power line frequency of 50 hertz is coming? Have you seen it, 50 hertz?
It's a little fluctuating
Yeah, so why this little fluctuation?
because of load variation on the power line.
But why 50 only? I can make another load. You can have 60 hertz. I can make some, impedance value such a way that it can be 100 megahertz also. Okay, you are right, but it's not answering the 50 hertz interference. So you are saying that because of the load variation, yeah, this value is changing. That's possible. That's correct. It's asking for some current, and it's fluctuating, so you may have some fluctuation. But this fluctuation may not be equal to 50 hertz. Why 50 hertz? Okay, I thought you know about this. That's why I didn't talk. Sorry.
The power line signal we are using in India is 50 hertz only. 50 hertz AC.
What about Europe? How do you know that it's 50 hertz only? Okay, my question is not actually this is just for fun I ask, but I'm not asking why 50 hertz. 50 hertz all because of what they are delivering us as power source, that is at 50 hertz. That has been like some standard. But the thing is, this is 50 hertz, but I'm saying that I have DC power line. So how this DC power line has 50 hertz? You yourself is saying that there is DC power line, but in India it's 50, in America 60, maybe Europe is also 50. So why is it so? How this, like you are saying that it's DC. If it is DC, why it's not DC? Why 50 hertz? I can understand that even though there is some DC line, but if I am connecting to some impedance which is moving here and there, so because of that it's asking some current. If it is asking some current which is small enough, but it might ride on DC value, which is the case for, let's assume that this is inverter. So this might happen. This is an inverter. Inverter is getting on and off, and it may couple at the input side. Right? This can happen. Right? I can understand this. What Subham is saying. So I'm not asking Siddhant.
No, sir. We are talking about the 50 hertz, like the frequency of utility. So how it is depending on that?
No, I'm not asking that. That derivation may be like Urvindi sir will tell you in a better way.
That so I like
Okay.
how utility frequency can affect this.
Look, this is the standard 50 hertz, and that is what we are generating through the that what you call fact, right? Fluctuating AC transmission line and what the studying that, right? Somewhere I don't know, but that is not my question. I'm saying that it's coming. Let's say AC 220 volt 50 hertz is coming, right?
Power
This is
frequency
there.
double the
DC power. He is talking about DC power, which is he want to use, let's say 100 or 10 volt, but it's not 10 volt. He is saying it's fluctuating.
because it might be derived from so it can the
So
fluctuation
not might be.
it
It's
will be
derived from,
yeah
yeah. So
AC source.
yeah. So what?
So that component
So that is what I'm asking. What is that component?
the ripple in the 10 volt depends on the prior circuit, like the switching frequency and the so on and so forth.
No, my question. Saurabh, you are saying something. Yeah. So you may have rectifier. In rectifier, we'll have, you know, if it is full wave, half wave,
So frequencies of
right?
100.
So this will be 100 or 50 hertz, right? So this might happen, but what we are doing, we are adding a big decoupling capacitor, right? So even though we do that, there are some ripple, and those ripples are there, and those ripples we are talking about, and this is known as 50 or 60 hertz interferences, right? So this was the thing I was asking, not
One question
huh.
on the AC signal is on 50 hertz, and we are converting that AC signal to the DC, and the fluctuations in the DC depends on the switching frequency of the DC converter.
Yeah.
So it shouldn't be like it
Exactly 50 you are saying.
Yes,
It may be 100, but even though it's 100, the general name of that interference is 50 or 60 hertz.
Okay.
The name of that interference, specifically because of this rectifier and all this ripple and all this, we are calling it 50 or 60 hertz, not 100 hertz, not 120 hertz, or multiple of
100, sir, we operate
or 25 hertz or some.
kilohertz, 10 kilohertz, 20, 35 kilohertz.
Okay. I understand that is also coming, but that's a different thing, right?
So it's nomenclature, like
Yes.
interference.
It's because of when you are converting this AC signal to DC, it's multiple of, because of the rectifier,
Mm.
this is going to happen, some multiple of 50. Even if you are getting some kilohertz, that kilohertz will be multiple of 50,
Mm.
right?
Yes.
So it's derived from here only, or because of this circuit we are calling it 50 or 60 hertz interferences. But when we are saying this is also known as common mode noise, by the way. So all analog engineers, they are calling it common mode noise. So common mode noise, if it is there, this is what we are saying, the power line noise is coming, which is 50 hertz, so superimposed on it. It might be power line noise 1 kilohertz superimposed on it, I can say that. But if I am saying it's 50 hertz interference line, may have some multiple of 50 hertz or some value, so that can be uh, there, and that is what we are trying to remove it. So if you are doing this 50, of course 1 kilo will also be removed, right? Because this is frequency. Okay, you can go with the derivation also, but it will give you same answer. Here it's 60 hertz because of America, this guy is American. Okay, so when you are doing all this, you can see that it's a minus 20 dB per decade slope in the sync function, right? This is also known to us. Okay, it is desired to build a 16-bit two slope integrating. When we are saying two slope is also equal to dual slope integrating type ADC, such that maximum input signal of Vin is equal to 3 volt, results in peak voltage of Vx being 4 volt. In addition, input noise signal at 50 Hz and harmonics should be significantly attenuated. Find the required RC time constant and clock rate. Also find the attenuation of noise signal around 1 kHz superimposed on the input signal. The question is very big, right? So you need to design 16-bit dual slope ADC with Vin equal to 3 volt and Vx being, so this is peak value. In addition to this, it's also 50 hertz interference. We want to remove this 50 hertz interference. Find the required RC time constant and the clock rate. And also find the attenuation of noise signal around 1 kilohertz. Now you can see, can you read the last line? Find the attenuation of a noise signal around 1 kilohertz superimposed on the input signal. So this is also considering another kind of noise, which is also because of 50 hertz interference only. Right? So we are using just two numbers like analog and mixed signal people, 1 kilo or maybe 50. Right? This is same what you are you know, or maybe you know the derivation better than me right now.
We are designing for the worst case, for the 50. Or maybe
Every time we are designing for worst case.
it is the nomenclature.
Yeah. Actually, when all power electronics are also designing everything for worst case.
Worst case only.
Yeah.
Like, sir,
We don't design anything for best case.
in SMPC, which like the processor is,
Mm-hmm.
from where the processor is getting the
Yeah.
power.
Power.
So in SMPC switch mode power conversion, we are operating that
SMPC or SMPS?
SMPS.
Okay.
Subject name is conversion.
Okay.
And
Conversion. Okay.
Supply, power supply is SMPS.
Mm-hmm.
Conversion we are SMPC.
Okay.
So we are increasing the frequency, switching frequency, to reduce the size of that SMPC because of the L and C.
Mm-hmm.
Because if inherently this ripple would be large, then we'll have to provide the more capacitance at the output
Mm-hmm.
to
Okay.
compensate that. So that's why we are increasing the frequency to lower down the size of the inductor and capacitor. So if the frequency is high, then that fluctuation would be less, and the frequency of that fluctuation would be the operating frequency.
So, do you know Vartika? Vartika, she is in MTech VLSI second year. So, what she is doing, she is also making one DC to DC buck converter,
Okay.
but she is not using inductor. She is using switch capacitor, and she is achieving something like 89% of efficiency right now.
89.
Worst case, I'm telling you. She is also doing similar thing, but our principles are different, and we want to make everything on chip. Otherwise, Vijender is one who is making buck converter, same thing, same specification, but with LC, where L will be outside.
Okay. That I have
Yeah,
seen in
yeah.
that college presentation.
Hmm. Basically, his motive is to make this such kind of like charger is outside, what we are seeing here.
Yes, sir.
That's all. So it's different approach, different application. If you want everything big, it's fine. If you want something smaller, it's different thing. Of course, like for processor, SMPS is very crucial thing. Then nowadays people want very small SMPS, right?
Mm.
And even targeting to have the entire SMPS on chip. Then yeah, that is what Vartika is doing.
That is for only the
Yeah. So she like that specification was given by ST. So she is in ST right now. She is doing her internship. She is developing some product which has not came yet.
and such as we are increasing the switching frequency losses increasing. That's
Of
why
course.
we are going to the resonance series converter. The water Ruben is taking.
Okay, good. It's a really very interesting subject. I must say that. Yeah. So what do you think? Did you get something? Sorry. Yeah. So T1 has to be 1 by 50 hertz, right? And that is going to give me R1 C1. But this is T1. Hmm? So, okay, 15 millisecond. But T1 has to be equal to 2 raised to n times T clock. N is already known to us, so you can find out T clock. Right? Right. So other things I have kept only for just for fun.
Last part is 2016.
Hmm?
Last
Last part?
calculation of the resonance.
Yeah, so it can be done at 1 kilo. So, right? Other things were only kept for fun, like all these things, just for fun. It's not useful.
The calculation will be like 20 dB per decade.
Yes, yes, 20 dB per decade. For a sync function, it's always right. Anyway, so there are some of the things which might be known to you. So there are few things which is not written in book, but in reality, that is what we need to do, because here the whole thing is depending on R and C. If we cannot integrate it properly, by the way, another name of such ADC is also integrate and dump. This is also another name. Some people in like companies, they are going to call such word. Some people are also calling integrate and fire. But the structure of integrate and fire is little bit different, but still it follows the same principle. It will have integration or RC. So the most important part is RC. So here the thing is, RC is the first block, and if R is changed by some delta R and C is changed by some delta C, you cannot actually remove the 50 hertz, or whatever you want to use as a sync function. Sync function advantage cannot be used. So for that we need to fix this value of R and C for a fixed value, right? So the best option is either of them you can uh, like choose to change. Fix one. Let's assume that this has been changed by C by delta C. So now we are going to tune R such that effective RC time constant will remain same. So in that case, what generally we can do, if we are changing R, we know that this delta C or delta R will be within 0.5 LSP. You have designed it such that it's, you know what is delta R or delta C. It was in your hand. So what you can do, you can keep some extra 2 or 4 or maybe 8 or maybe more number of some resistances which, which might be binary weighted. This might be binary weighted, or you can make thermometric weight, or many weights are available, and you can add actually some of the switches. I need to think, and so this resistance is available here. Okay, yeah, right. There are many other ways through which you can make same thing. We have undo. No. Something like this, and then capacitor is here. Let it be changed by delta C, no problem. But for that, like to change the switches, these are some B0, B1, B2, B3, and these are generated from here, where B0 to B3, whose input is actually coming from maybe output of this one, where you are measuring the frequency and you are comparing with the required frequency. So then you can do this. This is one way. Otherwise, you can tune C plus delta C. Rather than tuning this resistance, keep resistance where it is. And for doing all such things, you may have various compensation scheme you can use. You must be knowing about this. So these schemes are P, PI, and PID. You heard about this? These are also known as this gain control, lag compensator, and lead lag compensator. Right? You heard about this, right?
Yes, sir.
You are also using, right? So have you heard about PD, by the way, by some chance?
Differential function.
But have you heard about this?
Yes, sir.
Where?
But I have not used it.
No, nobody uses it. That's why I'm asking.
I have heard in literature.
Okay, so I'll tell you, you should not use PD ever. This is suggestion that one should not use PD because PD is dangerous. That's why it's P, PI, and PID.
Because we can manage that peak, but we cannot get the steady state. That will be control.
Sorry, I could not understand.
Differential part.
Mhm.
So differential part can manage the peak, how much it is going beyond this
Mhm.
level,
Yeah.
but it cannot get the steady state.
Yes. So you mean to say that whenever there is a derivative control, if there is some constant value, it makes it zero, right? Because derivative of some. So that is the reason we don't use just derivative, but integral can save you still. it can make you to reach steady state. However, the problem is it's going to give you sluggish response, right? It's things are very slow. But if you want to have both together, you can use PID. Generally, this is the way people are doing. But PD is dangerous. One should not use it. But PD can be used, or okay, this is just outside this course, but I'm just asking you. Let's assume that there is a D flip flop, right? And I need to tune these values Q and Q bar for a given time. So I'm doing time tuning. I wanted to have at some particular time, but it's not coming at that time. So in that case, should I use P type, PI type, or PID type? Or okay, this might be difficult at the beginning. Let's assume that there is a tank. Now there is a some sensor, or which is known as limit switches, through which you can, like, I'm supposed to feel this tank till this point only. So there is one limit switch. So whenever this point is touching here, this will become 1, and it will tell my valve to shut, and it will close this connection, right? How to control the behavior? Generally, we are not doing only this one, we are adding some controller also. That controller might be PPI or PID controller. So which control you are going to use now? Okay, why PID? That's the base one.
Because it has to close the wall very quickly, so its time response would be very fast, as well as
Okay, you are saying time has to be very fast. Okay, very good. What next?
the level is exactly like it is a digital kind of thing, or it is a margin like.
Yeah, so of course you will look, the whole thing we are going to make it digital. So we are understanding this in analog way, but this limit switches and all these things are generating digital 1 or 0, and there will be some margin. That margin is, of course, within half LSP, right?
Then it can be PI. Like if it is instant, then P only can.
Okay, so you are saying that, but still, look, this loop will take some time.
Then PI.
Look, so if this guy is telling him that please stop, till that time maybe extra 0.5 LSB will come. So still we need fast response. Look, after detecting this, if this whole loop is going to take more time, then this will also, you will have more LSBs, extra LSBs, or the leakage, right? So you need, of course, faster response.
Then PI can.
PIP, okay.
As it would reach the minimum of that level, and the level is keep on increasing. The integration, the controller will integrate how much.
Any instrumentation? Do we have any? Sandeep was instrumentation, but today he is not here. Right? Okay.
So controller will control by how much amount the level is increasing, and it
Okay.
will integrate that.
Okay, but we need to understand integrate is going to sluggish the response. This is one thing. So first of all, we need to understand why we are using P, I, and D. P for multiplication, gain control. I to get steady output where you want it. D again, like steady, like this was very low, so it can accommodate all the sluggishness created by integrator. We can do it with derivative. So here you are saying that if it is Pi, and understand one thing, accumulate something or remember something in general, which we are calling memory, then all these are equal to integration, right? So this particular tank, if I'm replacing with even a capacitor, even replacing with any memory or replacing with D flip-flop latch or anything which are going to remember the previous state, all are integrators. So if this is the case, we are not going to use ever pi, because integration is already there. You can control the time constant of this tank or maybe capacitor, resistor. These are the switches, look, and this is the capacitor. So RC time constant will tell you the integration time. You can control it, increase capacitor, increase switch, right? Through that you can do that, or you can change the dynamics of all these tank and valve, which is already inherent property of this system. So integration is already there. So in that case, you only need P, nothing else, right? So those system which has already integration inside its own system, then you don't need it. So like this one also only need multiplication at the time when it will work. It does not require, if it is some memory system or any digital system which is sequential, it does not require integration, right? So maybe in some mixed signal places you will find that it's a sequential circuit, so you are not going to add some extra integral or derivative action at all, right? Anyway, so you have to understand what kind of application you are using, and depending on that you can use dual slope or flash ADC. These are the two ADCs which we have studied. So now next part is actually successive approximation register. So we know about binary search algorithm. We are going to start with exactly half. We are going to start with exactly half. So if my input, so there are two terms, V in and Vref. Vref is actually the maximum available voltage. By the way, everybody have studied SAR, right? Somewhere, at least in your BTech, somewhere you studied, right? Okay. So you know that you are going to compare with Vref by 2. So which part of the reference value my input is available? Depending on that, I am going to decide. Let's assume that if my VDD is equal to 1 volt and my Vin is equal to 0.1 volt, and I have only possibility to use it for, let's say, 8 iterations are only possible. So then can you tell me the equivalent code, digital code? Are you following my point, right? So if Vin is 0.1 volt here, so where I'm going to go, like at the first point, so 8 iterations means like 8 bits. That is the meaning of this, first of all, right? So B0, so we are going to start from, when we are comparing this, is it comparison with MSB or LSB? Hmm? Okay, I made this numbering wrongly. It should be B7, B6, B5, B4, B3, B2, B1 and B0, right? So this comparison is at MSB level, because when MSB is 1, then like it's equal to Vref by 2. The input is around Vref by 2, little bit lower than Vref by, a little bit higher than Vref by 2. If you are here, then MSB is 1, rest of the things are 0. So here we are checking whether it's higher or lower. If it is lower, if it is lower, then you are going to keep that beat as 0, and you are going to make next beat equal to 1. So this is the first, actually this is the second iteration, I should say. So in this first iteration, what I have done, when I kept this as 1, it's Vref by 2, so it's measuring whether 0.1 volt is higher than Vref by 2 or lower than Vref by 2. So it's 0.5 volt, which is actually lower. If it is lower, then I need to make this bit to 0, make next bit to 1, raised to 0. For this, it will be what value? Equivalent value of Vref by 4. Vref by 4 is here somewhere, which is 0.25. So whether it's more than 0.25 or less than 0.25. If it is less than 0.25, then we are going to make this bit to 0 and keeping next bit to 1, which will be equivalent to Vref by 8, which is here. So Vref by 8 is how much? 0.125, right? So whether you are higher or lower, if it is lower, we have to make this bit to 0, next bit to 1, and so on. This will be Vref by 16. If you reach here, you have to check whether it's 0.0625. So it's more than that. If it is more than that, then you have to make this one as 1 and checking what is happening at next level of 1. For this one, you need to find out the equivalent code. So it's Vref by 16 plus Vref by 32. Right? And you have to do it till the last beat. If your output is more than the input, then you have to keep that particular beat as 1, next beat as 0, right? Is it, you have done it, right? This one in your BTech, yes or no? So through that you can find out the code. So that is what this whole successive approximation register or binary search algorithm does. But in reality, let's move a little bit higher than what you have studied. In reality, if it is a circuit where you have following things, you may have a comparator where there are two things. One is V in star, and you are going to compare something. This comparator is going to tell me that this value is with respect to input, whether it's higher or lower. So this 1 and 0 will tell me that what should I do with these 8 bits or these n number of bits. If this is MSB, if this is 1, so what should I do with that particular bit, whether it has to be 0, 1, that digital algorithm or a digital, you can say that I can draw finite state machine and you can find out how the circuit will look like, or you can always make the shift register. Right? There is always a shift register where first code is going in with 1, others are 0, then this 1 is always getting shifted, always right or left, whatever you like, right? And particular bit position you need to keep it 1 or 0, that will be also decided on this 1 and 0. Although shift register will always shifting this till the last point, and this 1 and 0 will tell whether particular bit has to be 1 or 0, right? So this is what happening, and when we are doing this, we have to store everything in some capacitors, this bit positions. So these might be whatever this 1 and 0, these might be each bit which are from maybe b0 to bn, which are going to convert this digital value to again some analog value, and that analog value will be compared here, that we are going to call it VDAC. Yes, Shashwat, right? So this is what happening in SAR. So this is what this block diagram says. Sample V in and make V D to A converter as 0. This is the first time when we are starting for the first iteration, right? For the first iteration we are doing this when we are starting, because V in star has to be compared with something. So this has to be 0. If my capacitors are charged to some value, the output will be wrong. And remember, DAC, although we have made so many capacitors and all, which you are also doing, but there might be some parasitic capacitors which might be extra. So that will also create some problem. So you have to make sure that everything has to be 0. So you have to keep one extra switch in shunt with all the capacitors, right? So these are some trick to design DAC or ADC, right? So let's read this flow chart. So what flow chart says: sample V in VDAC equal to 0, and this is the first iteration. Now I'm checking V in star at the first iteration, whatever is coming, it might be any value, 0.7 volt, or and some Vref is 1 volt. So everywhere VDD has to be 1 and this has to be 0. So 0.7 will be compared with 0. So output will be 1 or 0 depending on how you are connecting this minus and plus. Look, you are the designer, so sometimes you are connecting this to minus and sometimes you are connecting to plus. If you are connecting VDAC to plus, then output will be always 1, right? The first iteration will give you 1 only, right? And thereafter VDAC value will be something else, and accordingly you will have the 1 and 0. So here at the first iteration, when you are comparing VDAC is greater than V in compared with VDAC, so you are checking what is happening here. BI is equal to 1 or 0. If it is 1, then VDAC will have VDAC plus V reference plus I plus 1. As this is first iteration, okay, it's wrong. It has to be it has to be 0th iteration. Then you are starting with 1. So if it is 0, then it's Vref by 2, right? VDAC has already 0. Now you are adding Vref plus 2. If it is 1, if it is, so you compare first here whether it's more than 0 or not at 0th iteration, and then you know that of course that will be higher. So when it is 1, it's going to be here. My VDAC value will go to Vref by 2. But to make this, you need to make sure that accordingly all the bits will be generated. To make it Vref by 2, MSB is equal to 0 and rest of the things are 0, right? MSB is 1 and rest of the things are 0. And if it is less than this, which is not going to happen, right, at the first iteration, but if it is there, then it has to be minus Vref by 2. So let's assume that your input is 0.7 and this is 1. So 0.7 is somewhere here. So after first, this becomes second iteration. By the way, now I has been increased to 2. When it goes here, at that time you are checking with vref by 2 whether you are up or down. If you are up, means it's 1, and if it is low, it's 0. Right now it's 1. You are in this particular zone of the input. Now as I have to go up, I'll add vref by 2 more, or it will be something like 3 vref by 4, right? So 3 vref by 4, this was 0.5, and this is 0.75. Your input is here 0.7, right? So now at iteration 3, when you are coming here, it's 0, so you have to be here. At that time you should not change the bit. So earlier you were changing this bit to 0, but when you are saying that it's lower weighted, then you have to keep that value 1, right? Whichever value is coming, and accordingly you can follow the whole flow chart, and through algorithm you can find out the values of digital, right? Do you need some explanation on this, or are you following? Yeah, Siddhant,
Yes, sir.
what are you following, or you want some explanation, more explanation?
No, sir.
So here it looks like this, and we are going to call that particular circuit as successive approximation register, or SAR control logic. This can be designed by many ways. So there are many ways are available. We are going to follow, it's Alan Holberg book. So there is a solution is available how to design this SAR. However, if you are interested in finding out your own SAR logic, or your own SAR control logic, you can write down something called finite state machine. Do you know, right? Yeah. So
I have heard that,
you have heard, okay.
but
So
I never
okay,
understand.
okay, you never understand.
Only flowchart, but
Mhm.
how it works actually. Only flowchart I have seen.
Then what I can give you, I have some lectures on FSM recorded by myself. Okay, so this is the thing I taught to those BTech students who are learning digital with me. So through FSM you can design anything. This is, by the way, coming under automata theory. Some computer science people are studying this. So if you are going under automata theory, where you don't need to worry about, how this circuit will be generated, right? You are not, of course you need to write down somewhere kmap at the end, but this FSM. So I can tell you, let's make FSM. Okay, so following rules are there. Anything I am drawing in circle, that's the name of the state. Okay, so at beginning, if it is, if I am making just 4 bits, not, and there are two things. If you are seeing this arrow, and on top of that arrow there might be two informations, x comma y. One side x is, this is input, and this is output. So when we are starting, it's a reset switch, right? For 0 input, it remains staying there at same. But if it is next, which is 0 0 0 1, then what input or output is coming, you need to write down there, and that is how you can make the whole round of, you know. So there might be possibility with, or it might be possible, right? So after starting with first iteration, you may have possibility that this will happen or this will happen. One, you can avoid to write output also, because the next state is my output, right? You can invent, so there are many ways to draw these graphs. This is coming under graph theory, so this is a way you can write down, right? Now are you able to recover, right? So if the output is 1, this is going to happen, and if this is the one, this is going to happen. This will tell you that that particular beat has to be 1 or 0, and accordingly you can find out. This is a binary. When you are doing this, every time you are going to see two outputs. This kind of structure is known as BDD, binary decision diagram. This is happening because one reason, this is binary search algorithm. So of course you are going to have only one kind of graph, which is binary decision diagram, right? You will always have two. It's branching in two, right? This is what going to happen, right? Once this is done, you can name them as A0, A1, A2, A3, and you have to write down the complete table, that A0, A1, A2, A3, A0, A1, A2, A3. So there are two kinds of columns are there. This column name is current state, and this column of state is next state, and there is something called input. So by the way, this input in our case, it's coming from here, like these two are the inputs, or coming at the output of the comparator. This is input X, and our output is number of bit strings. So when you are doing this, you have to write down what is your input and what is the output. That output may have B0, B1, B2, B3, right? Are you following this thing? And you are following this also. So if present state is all 0 0, next state, if it is 0, you are at the same place. But if your present state is 0 and input is 1, the next state will change to all 0 1. By the way, A3 has to be MSB, right? So actually it has to be, I made it reverse way, right? You may have, right? So now how to write down output? That's the main important part, right? So output is also available with you, but to realize this, there is something called, if you have four different like if you have four inputs, means current state and next state, then you have to have, if you are designing JK, you are going to have 8 entries, because 4 J entries and 4 K entries. If you are designing with RS, 8 entries. But the easier thing, which we are going to use, all the digital people, they are going to use D flip flop. So you will have 4 entries. Let's call them DA0, DA1, DA2, and DA3. What these entries are doing? Till now, you are with me, right, Siddhant? Okay. Everybody are with me, right? Yeah. So Subham, you are laughing. So okay. No, no. Laughing is good thing. It's not bad thing, right? Okay. So if you know, so there are two kinds of tables are there. One is called state table where you know what is D, right? So if there is D flip flop, you know present state and next state. So if you know both the things, you can tell about next state, right? This is called state table, but there is some one extra table which is called excitation table. That will tell you if you know present and next state, which is generally known as qt and qt plus 1. If you're following some Maurice Mano book, then they are writing in this way. Then you can write down D. Similarly, you can write down JK, you can write down RS, right? So using that, you need to feed all these entries. Once you are done with this, DA0, DA1, DA2, DA3, you need to find out the K map. And then you can draw using all flip flops, because you will have, for 4 inputs, you will have 4 D flip flops, which you are going to call DA0, DA1, DA2, and DA3, which will have Q, Q bar, Q, Q bar, Q, Q bar, Q, Q bar, and all. This whole theory is for, by the way, synchronous circuit. So you are going to keep everything with some clock, and these has to be derived from here and there only. When you are going to get the answer, everything will be in terms of QA0, Q. So this is QA1, right? Using this, you can find out the final answer, right? You following? Like, I just gave some glimpse of what needs to be done. Otherwise, it will take almost one lecture, right? So are you following till now, right? And you can find out any circuit anywhere. If you stuck, you have to use finite state machine, which I have drawn, which you heard, but now you know at least something, right? You have not done it, that's why you are not confident, but when you derive it, you will understand FSM is the most easiest thing. There is nothing like anything difficult, I should say, right? You can design digital circuit if you know how the digital circuit will behave. If you know this behavior from the flowchart, you can make its circuit directly. Maybe it will take maybe 10 minutes. This was the question I asked last year, to draw the FSM for SAR ADC. Sorry, yeah, FSM, and derive the circuit from there. You can practice once. Right? If you are getting any difficulty, like, you have to follow what I told, but I can say that JK, RS, anything, but it will take more time. But just to teach you people, I think we should have at least one FSM. I'll give you at least one FSM in your exam, so that you will learn FSM. Otherwise, you will not learn. Will it be difficult, or Siddhant? If you wish, I can teach you. Personally, also you can meet me, or whoever wants to meet me, I can teach you. Right? Because this is the only way to learn. Otherwise, after exam, everything is done. It's also happened to me. If I want to learn something, I'm taking that particular thing to teach. If I'm teaching, I have to read it, and I can, solve it, and I can do the thing. If I'm not teaching the course, I'm not reading it. That is a problem. Right? Anyway, so in reality, whenever we are going to make the SAR ADC, our choice of selection might be charge scale DAC or the capacitive DAC. You can see that it's a binary weighted. In all 3 diagrams, it's same DAC, but let's see here. All these capacitors are binary weighted, right? So my goal is to, so I'm going to talk maybe next time, but the main goal here is, if my input is between Vref to minus Vref, it might be possible. You cannot have every time Vref to 0 only. you might be having the input signal ranging from plus Vref to minus Vref or 0 to minus Vref. This is also possible, right? In that case, how to get the output for a signed number? In signed number, we can have one extra beat, which is sign magnitude beat, the MSB. If it is 1, it's plus. If it is 0, it's minus. Something like this, right? That's what we used to do, if you remember, in microprocessor. Or so first beat is, or it's also known as flag, sign flag, right? So this is what we are going to do through the combination of jar scale ADC, so that we can have the signed output. So when can we have the next lecture?